It is with great pleasure that I open this session, dedicated to brain gene, ethnobotany, phytochemistry, and artificial intelligence in natural product research. I am pleased to have with me Professor Tibiawi and Professor Rouri as moderator reporters of this session, which promises to offer valuable insights and foster enriching scientific exchange. Now, please join with me in welcoming Professor Olivier Potterat from the Division of Pharmaceutical Biology, University of Basel, Switzerland, who will share insights on profiling approaches for discovery of bioactive natural products. The floor is yours, Professor Potterat.
So thank you very much. First, I would like to thank all the organizers for inviting me here. I'm feeling very honored to be part of this very nice symposium congress, and it's always a great pleasure to be again once in your beautiful country in Morocco. It's the first time in RABAT for me, so I'm very happy. Many thanks. So today I will show you a strategy we developed with Professor Matthias Hamburger of the University of Basel for finding new lead compounds in plant extract in particular. I mean, here in this audience, I do not need to stress the importance of natural products for the discovery of new drugs. You know, about 2/3 are directly or indirectly related to plants or microbes. But this is just half of the truth, because as you know, most major pharmaceutical companies, they have downsized or completely discontinued their programs with natural compounds. So there are many reasons. Professor Heinrich this morning mentioned some, but one is certainly that despite the very powerful methods we have, it's still very difficult to track the bioactivity in plant extracts, which are extremely complex. So what we have established in Basel is first a library. We have a large library of plant extracts which are prepared with accelerated solvent extraction, so it's a standardized procedure, and these extracts are stored in these small tubes at a concentration of 10 milligrams per ml in DMSO, and importantly, these small tubes are barcoded, and there is a database, so we can very easily have all the information together. And a very important point is that we can actually transfer very easily the samples and also the information which is linked to that. And this is the whole procedure. I mean, at the beginning we have this library in -80 degrees. It is stored. Then we have a robotic system. We can make replicates of these libraries. We can place this library for screening in our lab, but mostly actually in other labs with colleagues in pharmacology or biology in Switzerland or in other countries. And then you have, of course, we have about 3,000 of extracts, so you have possibly 5% hits, so it's quite a lot of samples. But we make a next step, and this next step, this is this HPLC-based activity profiling. It means we are just separating all these extracts into 30 fractions with the HPLC, and then we compare the profile of the activity with the chromatogram. And in this way, we can really select extracts which are promising for next investigation. We can already, it's made with HPLC MS, UV. We have already some data about the compounds which are included in this extract, and in this way we can really focus on the most most promising. Then, of course, you have the upscaling, more classical analysis or natural product chemistry, and you have the compounds. But this process is quite efficient to allow to start with a lot of compounds, a large number, and then at the end just a few ones for screening. Here, just one main instrument. This is this HPLC-MS instrument, which is connected to a fraction collector. So we just inject the sample. We can turn it here. You inject the sample, and you have a chromatogram, and you have then the activity, which is measured offline. But you can, in this case, you would say the activity is possibly compound 457, and you can then isolate these compounds. What we do, because you have a lot of, to avoid too much splitting, we make it once just with UV and the second time without collection in these deep well plates, but with the MS data online. So the advantages of this approach, you can use a large number of samples which are in these microtiter format. You can also use 96 or 384 format. The data and sample transfer is very easy, and this leverages collaborations. This is the main advantage. You can collaborate easily with pharmacologists and biologists. You use only, for the first steps, micrograms or milligrams amount of compounds, and you can make an early prioritization with plants. You know, plants very often contain tannins, and tannins are not really what you are looking for. So in this way, you can remove from your screen all these extracts. And reduce number of bioactivity tests. You have to test once instructions, but then you can work without this testing, and this is really a main advantage, because this step of testing again and again and again is one reason why this investigation of bioactive compounds in extracts takes quite a lot of time. So increased workup speed, and now I just want to show you a few examples where we have applied this approach and found some, I think, interesting compounds. And the first one was a collaboration with the ETH in Zurich, Professor Detmar, for searching for inducer of the lymphatic system. And you see here the library was screened. All these are the extracts here, and some of them were active, and this is the sprouting of these lymphatic cells, and we had actually quite a lot of interesting compounds. But why to search for compounds promoting the lymphatic system? There are some conditions like cancer where you want rather to inhibit these lymphatic systems, but there are also conditions, in particular this lymphedema, where there is an impairment of the lymphatic system, which leads to accumulation of macromolecules and fluids in tissues, which are not well drained to come back into the blood circulation. And this lymphedema is a situation which is a long life, actually lifelong conditions, and there is no cure for these conditions, so no treatment, and this is the reason why to search for such compounds which can improve the increased, stimulate the lymphatic system. And if we do it, we will be actually, it will be favorable for this lymphedema, but actually it could also reduce chronic inflammation and also improve the wound healing, in particular with diabetic wounds. This is the first example. I will show it very briefly, but it illustrates the strategy. These plants, we have an active extract, so we made actually the fractionation. You have the activity profile here, and this is actually the chromatogram beauty, and you can see these peaks is actually likely to be the active compounds. We could, in this case, we did not isolate these compounds. We just check in the databases and see that it is actually this chlorophyll degradation product, theophobite A, could be, we could get it commercially, it's commercially available, so we bought the compound, tested it, and that was it. I mean, the compound is probably not very promising, but it's a case where we did not need actually to isolate the compound, so it was quite efficient. But now I will come to another plant where we found, I would say, much more interesting compound. And this is a plant which is also cultivated in Morocco and also in Atlas, so Iris germanica. And this Iris germanica, if you see here, this is the proliferation of different cells. And these are here the lymphatic cells, and you see here this is the control, positive control, and black this is this extract. And it was very, it significantly activated, increased the proliferation of these leg cells, blood cells, or the here keratinocytes. They were not stimulated. So it was a specific stimulation of lymphatic cells. So we made further tests. These tests were performed at the University, at the ETH in Zurich, and this is the sprouting. So these are small microcarriers which are coated with leg cells. And if you consider here the sprouting here, this is the control here, and you see here with this iris extract, you can see the sprouts here, and this is here the quantification, and you see very micrograms per ml were sufficient to really strongly increase the sprouting of the leg cells. So the question was, what are the active compounds? And we used our approach, so we made here different fractions, and we tested these fractions. And you see here, this is the chromatogram here, and this is the activity here of the different fractions. Not only one fraction was active, like it's made very often the case, different fractions. And what we can say, these isoflavones are characteristic compounds in the iris plant, but no activity for the isoflavone. But the other group of compounds are these iridols. Iridols are triterpenoids, which are also very characteristic for the iris plant. So we then isolated a series of compounds. You have here all the structure. Many were known, a few of them were new, and you have also the activity. I don't want to go into details, but two of them maybe are interesting, particularly interesting. This one is actually not very active, but this is the first compound in this group, this class of compounds, where you have here a ketone and not aldehyde. And this one was, this iron pallidol was one of the major compounds and quite active, so it was selected for further investigation. And you see here some in vivo experiments. These ones were done at the University of Berkeley in the United States. And there was a pellet with this iron pallidol which was injected into the cornea of some mice. And then we followed actually the development of the lymphatic vessel in this cornea. And you see here the results after 14 days. And this is the situation here for the lymphatic vessels. So we control pallidol. Here you see a clear increase of the number of lymphatic vessels. The situation for the blood vessels showed that there was here no activation, so no stimulation. So again, we have here a situation where we have a specific stimulation of the development of lymphatic vessels. It's also shown here, the situation here for the lymphatic vessels with a significant increase, and in this case here, no significant increase for the blood vessels. Another test which has made here in vivo on mice, so it's the lymphatic clearance, and you can observe also how efficient this lymphatic system is for clearing compounds. So you have a mice, and the two here, the left and the right, and this one was treated with this iripalida, and this one was just the control, just DMSO, and you can see they were treated actually 8 days or 4 days before, and then you give this dye, and you see on the left hand side here clearly that the dye is much more faster and much more quickly actually cleared. So you have here an increased clearance, and if you make here quantification of many experiments, you get these results with the half-life of this dye here, and you see it is really reduced with the iripalida. So very efficient effect of this iripalida, not only in vitro but in vivo. Question was, what is the mechanism of action? First, protein kinase is this, the first one, does the iripalida interact with the VEGF receptors? And for that we tested actually these compounds. Here this is a VEGF kinase inhibitor, it's no compound, and you see here it has no effect. So you have here this is the increase of this sprouting of these neck cells, and even if you give these compounds, the sprouting will no effect actually on the VEGF receptor. Then protein kinase C here, and we did the same in this case, taking these PKC inhibitor here, and you see here actually decrease of sprouting means these iripalidal and these proteins then interfere with the protein kinase C, and actually this is something that is already known in literature, not all the effect on the lymphatic system, but with the protein kinase C. So it is a mode of action, and probably there is also another protein here, this GRP3. This has been found in a company which was working also on this compound in collaboration. So the next example is again a plant, I think, which is of interest here in Morocco, and also Heinrich mentioned also this morning this plant, saffron. And here it was a project with the Technical University of the Northwest Western Switzerland, and we found that the corms, we did not investigate the flowers, but the corms of these of saffron, they showed actually the extract of this corm showed a quite interesting activity on the secretion and also expression of different cytokines which are involved in inflammation. And you see here we have this extract, it was an ethanol extract, but in the saffron corms we have a lot of sugars there. This extract was about 80% sugars, polysaccharides, and also a lot of sucrose. I mean, saffron could be used to produce just sugar. It's really amazing how much sucrose, saccharose you find in these corms. But we could remove these saccharose just using a cartridge with HP20, and for the students here, if you want once to remove, you have an extract of a plant, there is a lot of sugars, you want to remove this sugar and to get only the more lipophilic secondary metabolites, just use the ion HP20. It works really well. You just need to have your extract soluble in water, solubilized in water, but you can have liters of water, and in this way you really remove in one step the sugars, like we did here. We had really, we got rid of these sugars and had a methanolic fraction eluted, which was much more active. So the methanolic fraction, this is the one which is here shown here, and this one was more active in these for these different cytokines. So here again, the question: what were the active compounds? And so we made again a profiling, made different fractions. In this case, the fractions were a little bit bigger, not 1 minute fractions, but we had this fraction, and we tested this fraction, and we saw that the activity was clearly here in this fraction 4, so we did our pool of these cytokines, and you see this fraction 4, this is this one, this is really the most active fraction. So next step was to isolate what we have in this fraction, and if you have a detailed look to this chromatogram, you see that we have something, we have nothing here at the UV 54, so you have nothing absorbing. It's not a polyphenol, but you have a very, very large peak in the ELSD, so evaporative light scattering detector. The detector indicating more or less the amount you have in your chromatogram. So we could, in this way, we could say we have a large amount of something which does not absorb anything at all, but which may be quite interesting. And so we made a lot of fractionation. It was quite complex, because you see at the beginning here, it was a fraction already obtained by preparative HPLC. It was really one symmetrical peak. You have the impression it's pure, but it's not. And making further HPLC separation, and here what we did, we had to change the chemistry. So we are the first, we use helic. Helic is also a good tip if you have relatively polar compounds. Like it doesn't work with everything, but with saponin, for example, it can work. You can use helic as, which is complementary to reverse phase HPLC. So you can use the same instrument, just reverse, starting with a lot of acetonitrile, increasing the water instead of the normal way where you increase the acetonitrile. But helic is a good opportunity, and then we had a good separation, but it was still not enough. And you see here we had actually 3 different chemistries which were combined to get at the end the pure compound, and there were 10 pure compounds, and here you understand why the separation was difficult. But you see these molecules are very big saponins, so the aglycol is the echinosistic here. You have this very unusual fatty acid residue, and so you have a lot of sugars. Some of them are not very common in saponins, like the fructose here. And the only difference in some compounds are the presence here of glucuronic acid or gallapuronic acid residue. So at the end, it's just a configuration at the position 2 of a sugar, which makes the difference. And for this reason, I'm quite surprised that we could separate them really baseline. But that was okay. And then we tested these compounds, some even still as mixture, and here you see on the secretion and the expression of Rantes was the cytokine with the activity, the most clear activity. But you see here these compounds which do not have all exactly the same activity. It's interesting, and so from a activity relationship perspective. So conclusion, saffron corn extract could be used possibly as topical agents. It's not something to be taken orally. It's saponin, glucoside, no absorption, but topically could be used in particular, for example, psoriasis or atopic dermatitis. Those are really diseases, conditions where these cytokines are involved. And I mean, this may lead to a valorization of these food waste, because when you cultivate saffron, you get a lot of these corns, which are just food waste product. And this could be actually a way to valorize saffron during the cultivation. So, and the last example will be quite short, not take too much time, but this is also something with sustainability. This time we are no more in the pharmaceutical field. It's more agrochemical research, but this is also a place for natural compounds to find substitute to pesticides, to synthetic pesticides, and a lot of issues with them. And in this case, it's to substitute copper. Copper is still allowed, even in organic agriculture, because it's extremely difficult to work without. And you have a lot of pathogens, fungi, and copper is extremely useful. Copper was actually in the 80s years, it was developed in France. The Bordeaux mixture, it was the first time one could really fight these new pathogens which had been introduced from the US, downy, mildew, and so on. And the copper is actually safe for human, considered to be safe, but there is a lot of problems with soil accumulation, toxicity to soil organism. So clearly here a need for finding a substitute which would be more friendly. And we, in this case, also applied the same strategy. We tested our whole library of compounds and actually found also some interesting extract with a promising activity. And here, one example, it was an extract of Magnolia bark. So again, in this case, it's a Chinese medicinal plant. This is a well-known plant, and in this case, if you apply this profiling here, you are clearly activity correlated with two male peaks, and not surprisingly, these male peaks were oniocule and manuliol, so not new compounds, not very exciting compounds, but the activity was interesting, and the goal in this case is not to find a fancy compound. The goal is to find something you can really apply, and if it's here, like this case, a medicinal plant, is already an advantage regarding the toxicity testing and so on. So the next step was to test these manual and monocule actually in seedlings and tomatoes, grape wine and apple were chosen, and in this case, I don't want to go into detail, but you see here, this is the extract, and here manual monocule, and there was a quite good activity, and the control was copper. Copper seemed more active, but actually good activity. So, and when you have something like that, the third level is actually the field trial, which is more challenging. You need, in this case, you need large amounts, so it has been done on grape wine because it was the plant where it was the most efficient, was less efficient on apple, for example. So we tested that. This is with the Institute for Organic Agriculture in the neighborhood of Basel. But the first time it was very new data, the first here, you see it was quite disappointing, so almost no activity. And this was due to the problem with the rain fastness. The problem with these natural products here is they are just washed out when it rains. And so we had to develop a formulation, and it's really a critical point. And with this formulation, this is the situation on the picture below. With this formulation, we had a quite good activity, and just due to the fact that we could avoid that just the product was washed out through water. This is one. We have actually also in this program, we have even a product I will not give too much detail, but with a plant from Indonesia, which is also in development. So I think here also for agricultural purposes here, the natural compounds are also a role to play. It's not only actually human health, as it's also veterinary medicine. It's also a very important field for medicinal plants today. Okay, so now just to conclude, so just to say a few words what we can do with this approach. I tried to show you quite really one fast, but the first advantage, you can test a large number of samples, and the more samples, the more extract you test, the higher the chances that you find something interesting. So the problem, if you have a few plants you test, it takes a lot of time. No, it's better you start with thousands of extracts and to increase your chances to find something good. And one word here, because I did not mention that when I spoke about our library. This library is, of course, Nagoya compliant, and it's a lot. There are a lot of plants coming from Panama. And this is something Professor Heinrich told this morning. So it's with Panama you can have very good collaboration, and then you can have access. It's really everything is well organized, but you need. We have no experience with Guatemala, but it's not the same with all countries. So we have a lot of plants of Panama for this reason, that we have excellent collaboration. With LTA agreements, which are really possible to do, and we can really plan for the next step if we have something which is really promising. Straightforward sample and data transfer is important. We can transfer just the data export as Excel file, and the place we can just with our small robotic system. We are not an industry, but this small system you can replicate or dispense all these, the full library within a few hours or days without risking to make ending mistakes. With this approach and the first HPLC separation, you can normally relatively efficiently locate, identify the potentially active compounds in an extract. This is a very important point. Then you can work without the biologist or the pharmacologist. It's not something against them, but if you have these tests at the beginning, then you are independent until you have the pure compounds. It's much more efficient. And at the end, we have the pure compounds. Maybe we have 10 or 20 pure compounds which are potentially active, and we say just please test. The 20 will not be active, but when everything is fine, you have some active compounds. So it's, I think, a good way. And these, let's say, see actually that it's the chances to find something interesting are quite high. This makes also collaboration attractive for pharmacologists and biologists. So it's also something which we always, the other people come to us and say we have a new test, we have a new target. Do you have something we could test against this target to validate also the target? So it's actually a good point. And because the goal at the end would be not just to make publication, it's always important for me as well, and it's the way it should also be done, but to find something which has really contribute to the improvement of a condition or a situation, and for that you need really compounds or discoveries which are really of high interest, and then we can make a patent application, and then we can of course the publication. So I hope I was not on time. It's okay. Okay. So thank you again. Thank you for listening. And okay, the acknowledgement. Many people was the homeowner, of course, and the last slide was the view of Basel. But, okay. Thank you very much.
Thank you so much, Professor Potterat, for this insightful and very, very rich presentation. We now have 2 minutes to have some questions. Are there any questions or perhaps comments for Professor Potterat? Yeah.
What can you say in terms of the replication? You came up with a known compound, which is interesting, the data are interesting, but how do you take this forward, or what yes or no decision would you be taking there? In terms of further development.
I mean, the importance is the available. I mean, the one main point is how available will be the plant material. So Magnolia officinalis, the bark, every bark is not the best thing, but for first steps it would be actually available in sufficient amount. Possibly here you could synthesize, but if you synthesize you have other problems because it's no more a natural product extract. And so for regulatory aspects, it's not the same. So Magnolia was okay. We have these other plants from Indonesia where it was resin. Actually, it was better. Resin actually produced in large amounts for perfumes and so on. So it was here we had actually a better situation. So availability. You mentioned that with a rare small plant, if you want to develop agrochemicals, it's a small plants which just grow in a small region in the mountains of here, Morocco. It's not good. Yeah.
Yes. There is a question? Another? Okay.
Thank you, Professor, for this nice presentation, and it's amazing the library you are developing. In Canada, I saw another library, but it's not about natural product development and screening. It's about really some drug impact and clinical aspect. And I was thinking, why not combine this? And what about the clinical application? If you just in this screening step, you go through after that clinical trials, and you can combine them, those data.
I mean, of course, this is the project with the iris plant. That was really the project these compound has been licensed by a major pharmaceutical company in Switzerland. And has been developed further, and it was actually at the level to be in clinical development. So really, and they did quite a lot of things, much more than what we could do. But at the end, it has not been put onto the market. It has even not been tested. And the reason is just that the company decided to change its strategy. So it was clearly the field of dermatology in this case. And they just said, no, dermatology is no more medicine area for research. We focus on cancer and so and other ones. So it's just, okay, stop, they closed the department, and for this reason, and this is what happens, unfortunately, often these compounds at the end are in the drawer somewhere, because they have been developed to a certain stage, and the companies don't want to give them free, you know? They just keep them, but that's it. And this is, yeah, but that's the way it is. And the pharmaceutical industry, of course, there are many strategic aspects. At the end, for us, it was very frustrating. Whether it was a good or a bad decision for the management of this company, I cannot say. But I can say this is what can happen, and then it's really a question of choice. You need to show some choice. Yeah, saffron would be something quite interesting. And but here again, you have this has been, there is no patent here. This has been published, and if somebody, I mean, making clinical tests in Switzerland is not easy. There are a lot of hurdles, and to find we cannot do that actually at the university is difficult. You need a company, and the problem you have here is again, they say, well, what is at the end, the IP, but maybe it's something to think about more locally, in other contexts, not seeing the big pharma also. Here there is no chances. Yeah? 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 Yeah?
One of the main process in, for example, cardiovascular disease is the inflammation.
Yeah.
And this is a very good discovery to work on in clinical aspects. So maybe you may collaborate.
Yeah, I mean, I would really think with saffron has more potential in the topical application, dermatology, psoriasis, atopic dermatitis, because these very large supplements, the bioavailability, if you take them orally, they are just hydrolyzed in the gut, and the bioavailability is really good. So I think it's a bit something for psoriasis. Atopic dermatitis are really conditions where there are no, I would say, satisfactory or fully satisfactory treatments.